Alright, welcome everybody. So today I'm going to talk to you about polarity. What we've seen before is that we have these molecules, they have a shape to them. Beyond having a shape, they have some resonance structures, they have formal charges. But one of the big things that really confuses people and gives them a difficult time is looking at polarity. And what confuses people, I think, most is the fact that there are polar bonds, which we'll talk about first, and then there's polar molecules, which also can be confusing. So when I look at a polar bond, what am I talking about? Well, I'm talking about this unequal sharing between two atoms. And this results in charges, partial charges, that can happen between two atoms. When I look at a bond, I'm looking at only part of a molecule. So for example, if I were to look at something like, CO2 here, so if I were to have CO2, and I were to look at each of these bonds, I would be looking at just this part of CO2 on the left here, and I would be saying, well, what is that bond? Is that bond polar or not? And the way that I do this is I look at the difference in electronegativity. So when I look at these two atoms here, oxygen has an electronegativity of 3.5, and carbon has 2.5. And so the difference between them in electronegativity, the difference in electronegativity is equal to 1.0. And so that means that we have this situation where the electrons are not being shared evenly. And in this case, when we look at this particular example, the O is pulling on the electrons more than the carbon. It has a higher nuclear charge, the same amount of shielding in this case, and so the way that we show that for the oxygen would be if we were to put in what's known as a partial charge symbol. And that partial charge symbol would be a negative with a delta sign for the oxygen and a positive for the delta sign for the carbon. All I can say at this point is that the bond is polar, that the difference in electronegativity between these two is large enough that they're not sharing equally, and yet they're still sharing the electrons. Now I could take another example here. I do HF. So HF down here, when we look at this, we have our H and our F. And when I look at the bond difference here, the electronegativity, the H is going to be 2.1 and the F is going to be 4.0. And so based on this difference here, the one that's going to be more negative is the more electronegative element F, and H is going to be the more not electronegative element is the H, and that's positive. Now, what you could also do with this is show it with arrows as well. So we sort of point at the negative element. So we can draw an arrow pointing towards F with a little plus sign at the end. And these two are used interchangeably. So like I could do it with the positive negative delta, I could do it with the arrows, I could show the dipoles in different ways. Now, as a result of this is called a dipole. Two poles, positive and negative. This unequal sharing is sometimes referred to as a dipole moment. You can actually calculate a value for this, but that's beyond what we need to be able to do for this course. Okay, so here's a chart of electronegativities. You can use this when you're doing practice problems. I have to see if the data booklet gives you electronegativities, but I would definitely know carbon, nitrogen, oxygen, fluorine, and chlorine, and hydrogen. I would know those 6, because they will really help you to, do things quickly, knowing their electronegativity difference, seeing how polar they are. Now, something else I want to bring out about being, a polar bond is it's sort of like a continuum. It's not where you just have, this is polar, this is not polar when we look at a bond. We sort of have, a gradual increase in polarity, a gradual increase in the ability for the electrons to be shared between the two atoms. You reach a certain point where they're no longer sharing. The one atom could be so electronegative compared to another that in fact you become ionic. So if I show you right here what these dipole moments look like, here are showing you 3 molecules, an F2 on the left, an HF in the middle, and an LIF over here. And so now we're going to look at, like what these three different compounds or molecules, or, particles look like. So if I look at the two, at the Fs here, each nuclei for the F is here and here. So this would be an F and an F. The blobs that you see here, yes, I use the blob word. The blobs that you see here, those show the electrons being distributed. When they're green, it means that there's no sort of buildup of electrons in one part of the molecule. So what does this look like here? Well, I have 4.0 and 4.0. So I have perfect sharing. They're both pulling on the electrons the same amount. And what that means basically is that my situation is where I am what they would call non-polar. I'm going to have to change the color here. Non-polar. Here's HF. Now with HF, the H is over here, and the F is over here. And the H has an electronegativity of 2.1, and this has an electronegativity of 4.0. And so what we can see, like we saw on the previous page, is that this is going to be negative and this is going to be positive. And we see that with the colors. The color blue represents positive, the color red represents negative in these diagrams. And then we have a situation over here where we have, and so this would be polar. We have a situation over here where we have Li and we have F, and we have something like 1.0 and 4.0. And now there's such a huge difference between them. Look at how the electrons are basically completely pulled from the lithium. And this would be ionic. And in here you have a negative and a positive, and they're charged ions. What we can do for the HF, instead of drawing the positive negative delta, we can draw an arrow. So now, when we look at the difference in electronegativity, again, you need to think of this as like, a gradual change from being sharing perfectly where you're nonpolar to where you are, ionic. They call it character, ionic or covalent character, to illustrate, the ability or the degree at which they're sharing. Now, the electronegativity, I hate these cutoffs here, but I present them anyway because I know that a lot of times you'll hear about this. But generally, if you're between 0 and 0.5 difference in electronegativity, you'll be nonpolar. If you are between 0.5 and 1.7, then you will be polar. And if you are between 1.8 and 3.3, the difference is really great. You'll be ionic. Now, I say take these numbers with a grain of salt. They are not set in stone. Look at HF above there on the screen here. HF, the difference is 1.9. It goes above that cutoff, yet it's still covalent. You have to look at each molecule and look at its properties. And we'll talk about the properties a little bit later on to give you an idea. Here's 4 more diagrams for you. And they're just showing you the degree of polarity, how they change. So over here, HF, we'd have the most polar. At the other end, the HI, we would be the least polar. And this has to do with their difference in electronegativity. Now this is, again, talking about the bonds, the bond polarity. And this is where things get a little bit crazy. When I have a binary molecule, that's 2 atoms. Well, those 2 atoms, they're deciding what the polarity of the entire molecule is. If I have 2 atoms, if I have a polar bond, that will give me a polar molecule. If I have something more complicated, though, I need to look at what's known as the charged symmetry. So let's take a quick look at what that is. So we talked about bond polarity, difference in electronegativity, but now what happens to an entire molecule if I have something with multiple bonds? So what I said before above is that, look, if the bond's polar, the molecule is polar, and this is only if you have a binary molecule. Well, what if you have an atom that has more than a molecule that has more than 2 atoms? Well, the way that I look at this is the symmetry of the charge. I look to see if it's symmetrical. And what I can see is that if it's symmetrical, in charge distribution, the molecule is nonpolar. Whereas if it is an asymmetrical charge distribution, it is polar. Now what do I mean by charge distribution? I mean exactly what I was showing up here on this slide. When we look at charge distribution, we look at how the electrons are distributed around the molecule. If they're spread out evenly, it'll be nonpolar. That's what we saw right here with FF. These electrons on the left here in the FF diagram, they are spread out evenly. Whereas with the ones down here, they're not spread out evenly. So that's the first thing I look for. How can I tell if something is polar or nonpolar? How can I tell if it has symmetrical or asymmetrical charge distribution? I look for a lone pair on the central atom. If I have a single lone pair on the central atom, it's going to guarantee that the molecule is polar. Two pairs work pretty much all the time. I can show you the chart on the previous page. If you are a bent molecule with two pairs, it definitely works. If you are T-shaped, if you are seesaw, then it definitely works. But there's some up above that won't work, and I'll show you that in a second. Here's also another diagram of showing you what I mean by charge distribution. So here we have CO2 on the left. We have two polar bonds, O with 3.5, C with 2.5. The O is pulling on the electrons more. It's pulling the electrons to the left, but on the other carbon, the other O is pulling the electrons in the opposite direction. We get this symmetrical charge distribution that I just circled down there. If we look at H2O, now the O with its 3.5 electronegativity is pulling on those H's electrons more. And the shape that we get with charge distribution is completely asymmetrical. Here's some other examples for you, showing you how the dipoles can do what's known as cancel. We can cancel the dipoles. And we see that with a molecule like CCl4, where the dipoles cancel. We see in a case where we have CH3Cl, they're not canceling, and you would have a polar molecule. So that's polarity for you. I just want to take a quick look at this chart right here and just run through if you're always polar. So back to the molecular geometry case, you will always be polar. Let me just change this to like blue. So something that's bent, always polar, has that lone pair. Something that is trigonal planar, always polar, has that lone pair. Something that's bent with two electrons pairs, they're on the same side, they're creating asymmetry, always polar. Seesaw, always polar. T-shaped, electrons on the same side, always polar. Then I get to this linear one. Look at how the electrons are arranged. They're not arranged symmetrically. In this case, you could be polar or nonpolar, depends on what's connected. Square pyramidal, one lone pair, always polar. And then we have square planar. Look at how the electrons are arranged. They're balancing each other. Depending on what's connected will depend on whether you're polar or nonpolar. We could have XeF4, that would be nonpolar. It's symmetrical. If I did XeF3O, that may lead to something that's asymmetrical and polar. We'll practice some of this in class. Thanks so much for watching. Have a great day.